I think we'll be able to finish this up. So titration of a strong acid, strong base, that's like Chem 1, Chem 20. And we did kind of rush through these, but really calculating the pH at any point throughout this is, do you have strong acid or do you have strong base? And these ones, it was a strong acid and then adding a strong base. So at some point, you're going to use up all the strong base. Your pH will be 7. And then after that, you're going to have the pH will just be calculated from the POH, because all of your sodium hydroxide will react with the HCl, or we could do, say, oh, I got to change that eraser size. That's going to get me. See, this is 0.025 moles of H plus. So H plus plus OH minus neutralizes, it makes water. So however much sodium hydroxide gets added in here, if you add 35 mils of sodium hydroxide at 0.1 molar, this is going to be 0.035 moles. And so it is kind of a limiting reactant. The 0.025 is the limiting, which leaves me with 0.01 moles of OH minus. If you take the negative log of that, yep. Can't do this. This needs to be the negative log of molarity, not moles. So 25 plus 35 is 60. So this is now the negative log of 0.01. 6 repeating, and that's molar. Oops. So that's 1.77815 POH, and now 14 minus that. There we go. That is 3 sig figs. Yeah. So don't forget to divide by the volume, because every time the volume does change, and that matters the more that you add. So strong acid, strong base is the easy one. It is that the whole time. At the equivalence point, don't forget that the pH, if both of them are completely neutral, then the pH is not negative log of 0. The pH is the negative log of 10 to the minus 7, because autoionization of water. So if you're doing the opposite, then you have a strong base and you're adding strong acid. Same thing in reverse. Again, don't forget to add the volumes and divide by the total volume. So do another one of these. So we have a 50 ml sample of 0.200 molar sodium hydroxide. We're trading that with nitric acid. We want to know the pH after 60 mils of nitric acid. So if we write out what is actually reacting, net ionic equation, if you will, take our 0.050 liters times 0.2 molar NaOH, 0.01 moles of hydroxide. Now, how much nitric acid did we add? 0.012 moles. and then treat this like a limiting reactant problem. Do we actually care how much water gets produced? No, because it's a liquid, so it doesn't factor into any equilibrium. But we do care what's left over after reacting. So my limiting reactant is hydroxide, which means that I'm subtracting that amount from both, and I'll get nothing there, 0.002 moles. Now I've got to take that 0.002 moles, and I need the concentration. Remember this when I did this one. So that's 0.01818 repeating molar H plus negative log is 1.740 pH. So based on these two graphs, figures which marker on the burette indicates the amount of base required to reach the equivalence point. Yeah, you gotta count, because the equivalence point means, and this is actually real important, equivalence point actually it's H plus moles equals OH minus moles, not concentration. And since the moles are the number of actual atoms in our solution, if we've got, 7 in here, then 1, 2, 3, 4, 5, 6, 7 hydroxides is what we need to add. So only when all of the acid's used up if you're titrating with a base, or only when the base is used up if you're titrating with an acid, do you get to the equivalence point. So you could ask the question like this: how much sodium hydroxide is required to reach the equivalence point? And I have 0.0250 liters of 0.100 molar formic acid, HCHO2. So this is 0.0025 moles. How many moles of sodium hydroxide do I need? Equal number of moles. Because the equivalent point is when these are equal. So at the equivalence point, I should have 0.0025 moles of NaOH. Because moles of acid are equal to moles of base. And then I have the molarity, which is moles per liter. So because these are both the same concentration, I need the same volume. Not milliliters, this liters. Yeah, just this volume. Again, volume at equivalence only depends on the number of moles. So what about weak acids? Weak acids are where we actually have a bunch of different things happening depending on where you are at in the titration curve. So if I want to calculate the initial pH, how would I calculate the initial pH? Well, it's my hydronium concentration. Is it though? So here I do have some weak acid. And so whenever I have just the weak acid or just the weak base, I do need to find the hydronium concentration, and then I would take the negative log of it. But this is going to dissociate some, but not completely. So we have to do an equilibrium, or use Ka. And as a refresher, remember Ka, well, at least for this, it's going to be H3O plus. I'm just going to use the generic A minus over the concentration of HA, the acid. So because I've got a small k, I can assume that this x is also going to be really small and doesn't matter. So 1.8 times 10 to the negative 4 is equal to x squared over 0.100. So 1.8 e to the negative 4 times 0.1. And then the square root, 0.00424. Let's do 26 molar 0 plus, because that's what x is. And then the negative log of that is 2.372. What are the units of the 0.01 here? On the ice table? Moles per liter, molarity. So here we can use molarity because we're doing equilibrium, so everything can be in concentrations. If I add some acid or if I add some base to this, then I want to figure out how many moles of the base reacts with how many moles of the acid, and then do a calculation. But since I haven't added any base, I just have the weak acid, I'm just doing concentration. This equilibrium ice table, like the last couple chapters. And that's going to be the case when you have all weak acid or all weak base. What's going to happen if I start adding base to this? We will have to calculate moles. And we enter a special region of the titration curve. So if I add some base, I'll convert some of my weak acid into weak base. And if I have weak acid and weak base in the same solution, it's a buffer. So adding any base to this, or any small amount of base, as long as it doesn't completely use up the acid, will enter into the buffer region. And then when I get to the other side of the buffer region, I'll almost the same calculation, except instead of being all acid, I'll have converted it all over to base. So the buffer region's bookended by this calculation, essentially. So if we add a little bit of base, now we have a buffer. And actually, this is the easiest place to do calculations. So down here, not in equilibrium ice table, but just showing that if I add in some base, that base is going to react with my acid will be converted into base. Which means that pH in this region, since I now have a buffer, I can calculate the pH with the Henderson-Hasselbalch equation. A couple things that are nice about this. The volume doesn't matter because I'm dividing either the concentration or the moles by concentration or moles. And so the units completely cancel out because both of them are in the same solution. So if I do include the volume, if I do calculate molarity, then the liters will just cancel. So I can do it with just moles. And then we do need the pKa. So negative log of 1.8 e to the negative 4. So pKa is 3.744727. Log of my base over the acid. No. Because if I do calculate the molarity for both, I'm going to divide both of them by the same volume. And so it cancels out in the calculation. Definitely recommend just like do both. Put in moles, put in molarity. Prove to yourself that it's the same. So pH is 3.14. 143. So how do we know we can use the Henderson-Hasselbalch equation? Because you're in the buffer zone. How do you know you're in the buffer zone? Yeah, where we have acid, we have the weak acid and the weak base.
So you keep saying weak base, but all these slides are labeled strong base.
Oh, this is the weak base.
Okay.
So the weak acid and its conjugate, weak base. So yeah, when we add some strong acid, we convert some of our weak acid into weak base. Yeah. You can think about this as like the adding strong base just changes the starting point for your calculation. It's just moving some of the acid over to base, start calculating from there. Throughout kind of all of this. So if we continue to go through here, we have adding more of the strong base, which every time takes more of my weak acid and converts it into weak base until it's almost gone. And that's the entire buffer region of the curve. So all of these points relatively level in terms of pH. But if I add 5 more mils, and these are cumulative mils of strong acid or strong base added, Right, so the 10 mils is including the 5 mils from before. We're up to a total of 20. Oh, and you can find the pKa. So if you didn't have the pKa or the Ka, you could find it if you knew this point, because the pH is equal to the pKa when the moles or the concentration of the acid and base, weak acid, weak base, are the same. It's not the equivalence point. The equivalence point is when I've neutralized all of my acid. But it does tell you what the pKa is. And Henderson-Hasselbalch works for all of those. But it only works as long as you have weak acid and weak base. So if I do 25 mils of sodium hydroxide, 25 mils of strong base, then I have neutralized all of my acid, and now it's all base. So to calculate, I can't use the Henderson-Hasselbalch equation. For one, it'll give you undefined because you'll get acid divided by base, or base divided by acid, and acid here is 0. So you can't divide by 0. But we can use equilibrium. Oh, actually, we need to use, yeah, okay, it is just on the next slide. So we can't use, I'll write this in. So if I tried to use Ka, Ka is for this equation. I want to put 0.00250 into there. But what's my concentration of, or my moles of acid? That would be what we're trying to find. So I cannot use this Ka equation. I need to use Kb, or the Kb equation. Figure out how much base is produced. So this would be the equation for Kb. And we also need things in terms of concentration. So how do I calculate Kb? It's two ways. Ka times Kb equals Kw. 10 to the minus 14 is Kw. So Kb is equal to 10 to the minus 14 divided by whatever your Ka is. So 10 to the minus 14 divided by 1.8 e to the negative 4. So Kb equals 5.55 times 10 to the negative 11. And then we do an equilibrium ice table starting with all of my weak base. So x squared over 0.05 equals Kb, which is 5.555, repeating, times 10 to the negative 11. So times 0.05 square root. That's a small number. It's probably 6,6 repeating. But that's not H3O plus, that's OH minus. So the negative log. So 5.7781 equals POH. 14 minus that is 8.222. So beginning of this titration, we did equilibrium isotable, Ka with the weak acid, because all we had was weak acid. Then anything in the buffer zone, Henderson-Hasselbalch equation. When we get to the other side of equilibrium, and this is literally just at the edge of the buffer zone when you've run out of the acid and you have all base now. And by all base, I mean the weak base, conjugate of the acid. Then we do another ice table, but we have to do that ice table with Kb because now we've got the weak base. So I need the Kb for that weak base so that I can find OH minus and then eventually convert that into pH. That one's probably the most complicated. And if we add more strong base to this, now it's the same as we talked before about adding a strong base to a weak acid, or to a weak base, strong base to a weak base. Only the strong base matters. Only the strong base determines the pH. So as I add more to this, now I've got, so adding 30 mils of sodium hydroxide. So there's the 0.003 moles that we added. Subtracting that, now the weak acid is my limiting reactant, which means I have some leftover strong base. I do have all of this weak acid, but if we were to calculate out how much base, how much hydroxide comes from the weak acid, it's going to be really small compared to the strong base. But we do need to be able to do POH. We need to figure out what our concentration is. So divide that by the volume, which is 0.055 liters. So that's 0.009. What is with all these repeating numbers? Molar OH minus, negative log, and that's 2.04139, but that's POH. So 14 minus that. $11.959. What happens if we add more strong base? If it was a diprotic acid, then we'd hit the next buffer zone. This one just is a monoprotic acid. But yeah, if we were to hit the next buffer zone, and if we hit exactly the edge of that buffer zone, then we would need to use equilibrium again. And then you could use Henderson-Hasselbalch throughout that buffer region. And then if you got exactly to the other side of that, then you could use equilibrium again, and then you would keep going with POH. But because this is monoprotic, we just keep going with POH. So every time I add more strong base, I basically add that to my previous strong base that was left over and calculate pH again. So calculate POH, then pH. So the overall curve and the points to really know are this initial. So this is all weak acid. There's no weak base yet. I haven't added any base. It's just the concentration of the weak base. Throughout the buffer region, so all the way from that initial point up to the equivalence point. Yeah, up to the equivalence point. That's the Henderson-Hasselbalch buffer range. At the equivalence point, it's all weak conjugate base. This is the one where you have to, I guess the first thing you have to do is calculate Kb. Then 2, you calculate OH minus. And 3 is you calculate pH. For a monoprotic acid, once you're past that, then it's all the OH minus that's in excess. I guess technically you could do equilibrium throughout the whole thing. The key is though, as soon as you get to this buffer, or as soon as you get to the equivalence point, it still has to switch from the Ka equation to the Kb equation. That makes sense. All right, so if we have a 40 ml sample of nitrous acid titrated with potassium hydroxide, calculate the pH at the equivalence point. So how do we even start this? I think first, like, what is equivalence point? When the moles are equal.
Calculate how many moles of nitrous acid we have.
Mm-hmm. Take how many moles of nitrous acid. Similarity 0.0040. I think there should be another 0 on there. Moles, HNO2. So base is equal to the acid, so I need that many moles of base. So at the equivalence point, that's going to be 0.0400 moles of strong base, KOH. And so then I need to figure out how much of that I'm adding. So 0.02 liters
convert equivalent point in KB instead of KA?
Yeah, so at the equivalence point, that means that I've converted all of my weak base, sorry, my weak acid into weak base. So also, I have 0.00400 moles of NO2 minus. So Ka times Kb equals Kw. So 10 to the minus 14 divided by 4.6 times 10 to the minus 4. So Kb and the reason that I need that is because if I don't have any weak acid, I don't have any leftover strong base, then to calculate the pH, I have to calculate it for the reaction of NO2 minus plus H2O is OH minus plus HNO2. That's the Kb equation. And then the reason that I needed to calculate the volume of KOH is because that's going to determine my volume at this equilibrium. Because I have 0.04 moles of nitrous acid, or I guess nitrite, but I need concentration for equilibrium. So 0.004 divided by 0.06. NO2 minus. This is going to be 0, 0, but they will be x, and this will be 0.0667 minus x. So now x squared over 0.0667 equals 2.1739 times 10 to the minus 11. So x is 0.3451204, which is molar OH minus. So negative log then is 5.9193. 14 minus that. pH is 8.0806. That's way too many. 8.08. Yeah. Kind of a lot. All right. Well, we'll continue on Wednesday.